Our next skill involves finding the volume of the solid of revolution. Before we get into the examples in the stew packet, we're first going to take a couple minutes to introduce what a solid of revolution is. Take a look at the screen in front of you. You've got an area that's bounded by the graph of y equals the square root of x on one side. That's the top curve. You've got the x-axis on the bottom side of this region. Remember, the equation for the x-axis is y equals 0. And we got two vertical lines. We don't really know the numerical values of these vertical lines, so we're just going to call them x equals a and x equals b. Now, just like the name sounds, if we rotate or if we revolve this shaded area around an axis, well, we're going to have a solid formed. This time we're going to rotate around the x-axis. Let's take a look and see what this graph will look like. Okay. You can see that we get a solid. Looks kind of like a watermelon that's been sliced in half with one end cut off. And we're going to talk to you about how to find the volume of this solid. And we're going to give you a generic conceptual approach to setting these problems up. We're going to say that the volume is going to be the integral from a to b of the area function. When we say the area function, we're talking about the area of the cross section. Now, if we have a vertical axis of revolution and a horizontal axis of revolution, we'd have a slightly different looking setup, just because sometimes we'll integrate with respect to x and other times we'll integrate with respect to y. And just a few examples will clear this up for you. When it comes to solids of revolution, there are two types of cross sections that we can run across. One is a disk and the other is a washer. Let's take a look at an example of each. Let's take another look at this example. If we rotate the area of a shaded region around an axis and the cross section gives us a circle, then we're going to use the disk method. However, sometimes we're going to take an area, rotate around an axis, and we'll get a cross section to be a circle with a hole in the middle, which we're going to call washers. Here's an example of a washer cross section. You notice now the axis of revolution has been moved from the x-axis down to the line y equals -2. As the shaded area spins around the axis, we get a solid generated that has a hole, it looks like, that has been drilled through the middle of our solid. And now let's put this all together. When our cross section is a circle, we're going to use the area formula for a circle. When the cross section is a washer, actually an annulus, but we're going to use the washer method, we're going to need to know the area formula for this circle with a hole in the middle. When writing the radius of a big circle and a small circle, we're going to let capital R represent the radius of the big circle, and we're going to let lowercase r represent the radius of the smaller circle. Now, let's put this all together. The volume of a solid with disk cross sections is going to be found by taking the integral from a to b of pi times some radius function squared with respect to x. And you know pi is a constant, so you're frequently going to see this formula written as volume is pi times the integral from a to b of the radius function squared dx. You see, we just took the constant out in front of the integral. Now, looking at the washers, you're going to see the same type of setup. You can see that the volume is found by taking the integral from a to b of pi times the big radius squared minus pi times the little radius squared with respect to x. Now, since there's a constant multiple pi in each term, we can factor out a pi and say that the volume is going to be pi times the integral from a to b of the big radius squared minus the little radius squared. So now, one question that you might be asking is, why do you call radius r of x? Well, the radius is a function of x, and we'll show you what we're talking about. You see in this area diagram, if you're going to represent the radius going from the axis of revolution to the end of the shaded region, if we draw the radius out far away from the origin, in this example, our radius seems to be pretty lengthy. But if we drew the radius segment from the axis of revolution to the end of the shaded region near the origin, our radius is quite a bit shorter. So you see that the length of the radius changes as x changes. This means that the radius is a function of x. And we'll express the radius as r of x, the radius as a function of x. Okay, so now take a look. The cross section that you see here is a solid circle. There's no hole in the middle. I had trouble writing there. Solid circle. So we'd use the disk method. Okay. In this particular example, we can say that the volume of the solid is going to be found by taking pi times the integral from 0 to 9 of the radius function. Now in this case, well, how do you define the radius? One way to define the radius is to draw the radius segment from the axis of revolution to the far end of the shaded region. And again, the axis of revolution was given to us. It's labeled in the diagram. So now let's take a look. What's the top boundary of the radius segment? The top boundary of the radius segment is our function, y equals root x. So we can determine that r of x, in this case, is going to be the top, root x, minus the bottom. What defines the bottom of our radius segment? Well, that's the x-axis, and the x-axis has the equation y equals 0. So top minus bottom. Our radius function is going to be expressed as square root of x minus 0. Oh, we know this is just root x. So now we go to our integral. We're going to integrate the radius function squared with respect to x. And the radius function we found was root x. Let's look at one more example. Down here, you can tell now that what we're looking at is not a solid circle. We're looking at a circle with a hole in it. You can see here, there's a hole drilled through the middle. The cross section that we're dealing with shows a circle with a hole cut out of the middle. So we're going to use the washer method. We're going to need to identify two radii. Okay, let's darken this axis of revolution. Axis of revolution is y equals -2. Now let's draw the radius. Let's draw the radius. We're going to have two radii. First, let's identify big R, the big radius. This goes from the axis of revolution to the far end of the shaded region. Let's set up an expression. Big radius is going to be the top. What defines the top of this big radius? It looks like our curve defined by y equals the square root of x. So we have square root of x minus top minus bottom. What's on the bottom of our radius function? Well, it looks like we have the axis y equals -2. So we're going to have big R of x is root x minus -2. Well, cleaning that up a little bit, becomes root x plus 2. If you think about it, that kind of makes a little bit of sense, because in the previous example, our radius went to the x-axis. And now we've added 2 units to the length of the radius. And now let's find the little radius. To find the little radius, we draw a segment from the axis of revolution to the near side of the shaded region. Okay. Let's set up an expression to represent the little radius. Once again, we'll do top minus bottom. What's at the top of the radius segment? It looks like we are at the x-axis, or y equals 0. So minus. Now, what's at the bottom of our radius segment? Well, it looks like we can call that the horizontal line y equals -2. So once again, 0 minus -2 is really just 2. You can tell that the little radius is constant. That's why there's no variable in the expression. Now, to set up our volume integral, we would say the volume is going to be pi times the integral from 0 to 9 of the big radius function squared minus the little radius function squared. Okay? The big radius, we said, was root x plus 2. It didn't turn out very clear. Let's write it again. And then the little radius, we said, was 2. There you go. Here's our setup. For the first day, we're just going to focus on setting up integrals. Later on, we'll focus on setting up and evaluating integrals. Well, hopefully this introduction helps you understand what a volume of a solid of revolution is. Now we're going to go to the STU packet and do a couple examples. It should clear things up for you. Thanks for watching the video. If you have any questions, bring them to class. Bye-bye.